Welcome. In our last lecture, we learned how to estimate, how to calculate the traffic, storage, and bandwidth a system needs to handle. But estimation is just the first step. Once you know your numbers, you need to make commitments based on those numbers. So, and in software industry, we make those commitments through something called SLAs, SLOs, and we also have SLI. So what actually these are? SLA stands for service level agreements. It is a kind of contract which we sign before developing a software product, and we sign the contract with the customers, right? So and SLOs, it is a service level objective which we want to meet, and we want to achieve this objective. We want to make a promise with our team, not with customers. Like we have to achieve this goal, right? In order to achieve SLA, we have to set high SLOs. And then we also have SLI, which stands for service level indicator, which usually tells us that you need to take quick action in order to meet your SLA and SLOs, right? So later on we will be talking about each of them with examples and with more details. And these are not just corporate documents, they are the engineering contracts, and that determine how your system is designed and how your team is measured, and whether your company keeps its customers or not. And look at the table at the right side. You can see that these are the availability nines. At 99% availability, your system is down for 3.65 days per year, right? And at 99.9% uptime, your system is down for 8.7 hours per year. And similarly, at 99.99% of availability, your system is down for 52 minutes per year. And as we increase the number of nines, so the downtime of the system decreases. And here, if we have the availability 99.999%, so then we have the downtime 5.2 minutes per year, right? So each one of those numbers is completely different architectural problem. And by the end of this lecture, you will understand the difference between SLI, SLO, and SLA. And you will know what an error budget is, and you will be able to write proper SLOs for your own systems. So let's begin. Alright, there are three terms here. People use them interchangeably, and that is a mistake. They are very different things, and the difference matters. Let me start with SLI. SLI stands for service level indicator. So let's understand what is actually service level indicator. And SLI is a measurement. It is a number that describes how your system is actually performing right now. It could be the percentage of HTTP requests that returned a successful response, or the percentage of requests that completed in under 200 milliseconds. Whatever you are measuring, that measured number is your SLI. Notice the example over here. 99.2% of requests in the past 30 days returned HTTP 200 in under 200 milliseconds. So that is specific and that is measurable. So that is an SLI. Now let's talk about the SLO. SLO stands for service level objective, and SLO is a target. It is the value your SLI must stay above or below. For your system to be considered healthy, your SLO is an internal promise. Your team makes it to itself and to the rest of organization. And here in the example, the SLO says your SLI should be at least 99.5% over any 30-day rolling window. If the SLI drops below 99.5%, so the team has breached its own objective, and that is a signal to stop shipping new features and fix reliability, right? And now finally, let's talk about the service level agreement, SLA. And SLA is a contract. It is a formal, often legally binding promise you make to your customers. If you breach it, there are consequences, refunds, service credits, penalties, right? So the critical insight is this: your SLO must always be stricter than your SLA. You always target better than you promise, right? So that gap between your SLO and your SLA is your safety buffer. If your SLA promises 99.9%, so your internal SLO should be a 99.95%. That way, if your team misses the SLO slightly, so you still keep your SLA promise to the customers. SLI is the measurement, SLO is the internal target, and SLA is the customer contract. So that is the hierarchy. Alright, this table is something every engineer should have memorized or at least kept somewhere within reach. Let us walk through it. At 90% availability, we have 19, right? And your system is down for 36.5 days per year, which is equivalent to 72 hours per month, right? And this is unacceptable for almost anything customer facing. This is the level which is appropriate for internal tools that people only use during business hours. And at 99% availability time, we have 2 nines, right? And our downtime is 3.65 days per year, and this is acceptable for small apps with tolerant users and a side project or an early stage startup, but this is not suitable for production like software as a service product, right? And then we have at 99.9% availability, we have 3 nines, and the system will be down for 8.7 hours per year, which is equivalent to 43 minutes per month. This is where most serious software as a service product operate, and it is achievable with standard deployment practices and basic redundancy. At 99.95%, we have roughly 3.5 nines, and the system is down for 4.4 hours per year, and this is the standard commitment you will see from AWS, Google Cloud, and Azure on most of their services, right? At 99.99%, we have 4 nines, and the system is down for 52 minutes per year. This is less than a minute per month, and this is the target for financial systems like healthcare platforms and serious B2B products, where downtime has direct contractual consequences. And at 99.999%, we have 5 nines, and the system is down for 5.2 minutes per year, which is less than 30 seconds per month. And this is the world of telecoms, payment rails, and air traffic control system. Let me try again. And this is the world of telecoms, payment rails, and air traffic control systems. Now look at the most important note at the bottom. This is one of the important note. All right, let me try again. Now look at the note at the bottom. This is the most important lesson on this slide. Each additional line roughly multiplies the engineering cost and operational complexity by 10. Going from 3 nines to 4 nines is not a configuration change. It is a completely different architecture. So you need active multi-region deployments. You need zero downtime deployments. You need automated failover. You need on-call rotation and incident response processes. So the right availability target is not the highest one you can think of. It is the one that matches what your business actually needs and what your team can actually sustain. Alright, this is the concept that changed how I think about reliability, and it came from Google's site reliability engineering team. It is called Error Budget. Here is the idea. Your SLO says your service must be available 99.9%, right? And that means 0.1% of the time is allowed to be unavailable. That 0.1%, that is your error budget, right? So it is the amount of unreliability you are officially permitted to spend. Look at the two examples. At 99.9%, your error budget is 43 minutes per month. That sounds small, but 43 minutes per month is actually quite a bit of room, and you can deploy risky changes, you can run experiments, you can accept that some releases will have minor issues. As long as the total downtime in the month stays under 43 minutes, so you are fine. And at 99.99% SLO, your error budget is 4.4 minutes per month. That is almost nothing. Every single deployment becomes high stakes, and you cannot afford a bad release. Feature velocity drops dramatically. So now look at three rules over here on the right side. This is how error budget actually work in practice. Rule number one, when your budget is healthy, ship faster. If you are only halfway through your error budget for the month, that is a signal that your system is stable and you can take more risk, deploy more often, run more experiments. And then we have rule number two, when your budget is exhausted, freeze features. No new code goes to production until the error budget resets and the team shifts entirely to reliability work. This is the Google SRE model, and it is brilliant because it creates an automatic break, right? And then rule number three, error budget align incentives between product and operations. So product teams want to ship features fast, and operation teams want stability. These two goals are always in tension, right? So the error budget makes the trade-off explicit and numerical. There is no argument. The budget is either available or it is not available, right? So this is one of the most powerful tools in modern reliability engineering. Learn it and use it. Let me try again. So we need to properly learn it and then use it. All right. Let us look at how three of the world's best engineering organizations actually write their SLAs. First, we talk about the Google Cloud Storage. Google promises 99.95% availability. If they miss it and fall between 99 and 99.95%, so you get 10% of your monthly bill back. If they fall below 99%, you get 25% back. But here is the important part. Google's internal SLO is 99.99%. That is 4 times tighter than what they promise with customers. Why? Because they got the gap between 99.99 and 99.95. There is a safety buffer. If the system degrades slightly, they break their internal target, that the team gets alerted and they fix it, and the customers never even notice, right? So the lesson is that your SLO should always be stricter than your SLA. And your SLA basically you promise with the customer, and in your SLO you promise with yourself. So design the gap deliberately between the SLO and the SLA. Now let's talk about the AWS S3. Amazon Web Services S3 promises 99.9% availability on S3 standard. But look at what they say about durability. 99.999999%. That is 11 nines. That is a different metric entirely. So this is a crucial distinction. Availability means can you access your data right now, and durability means will your data exist tomorrow. These are different questions and they need different SLOs, right? So AWS separates them completely. When you design your own systems, you need to be just as precise. Define availability and durability separately. And then if we talk about the Stripe Payments API, which promises that 99.9% availability will be ensured on their payment API, that is four nines, right? And the level appropriate for anything that handles money. And your internal SLO includes not just availability but latency as well. And payments must complete in under 500 milliseconds at the 99th percentile. That is the key insight from Stripe, right? A slow payment is almost as damaging as failed payment. If a customer's credit card takes 10 seconds to process, they assume something went wrong and they try again and they get charged twice. So you have a support nightmare. For any system where response time is part of the user experience, which is included in most systems, you need latency SLOs alongside availability SLOs. Alright, now I want to show you something very practical, the difference between a bad SLO and a good one, right? So most of the SLOs I have seen in my career were bad, not because the teams were incompetent, because nobody had told them that a good SLOs actually looks like this one, right? So here is the formula. At the top you can see a good SLO must have four parts: the SLI metric, and then we have the threshold, the window, and the measurement method. So if any of these four parts is missing, the SLO is unmeasurable, and an unmeasurable SLO is worthless. So let me go through the three examples. Here you can see three pairs. The first pair, which demonstrated on the left hand side, this is the bad SLO, and on the right hand side we have the good one, right? So API should be fast. This is bad SLO because that tells me nothing. Fast for who, under what load? How do we even know if we are meeting it or not? So there is no measurement, no threshold, no window. That's why it is not a good SLO. And a good one would be 99% of checkout requests complete in under 300 milliseconds, measured over 28-day rolling window. Now I have everything I need. I know the metric, the threshold, the endpoint, and the window. So I can instrument my system. I can build a dashboard, and I can be alerted when it breaches. Then we have the second pair, and we have bad SLO on the left side, and it basically tells us that service uptime is 99.9%. What is uptime? Is the service up if it is responding with errors? Is it up if only one of three regions is working? So again, it is not clear. There is no measurement, so we can't say this is a good SLO. And on the right hand side, you can see that 99.9% of the health check probes return HTTP 200 from at least 2 of 3 regions per calendar month. Now there is no ambiguity. I know what is being measured and how it is measured, right? And if we talk about the third pair, on the right hand side you can see that no data loss. And so again, this is the bad SLO. How do you measure no data loss? This is completely untestable as written. So a good SLO would be a recovery point objective equals 5 minutes. The last committed write is recoverable within 5 minutes of any failure. That is specific, testable, and meaningful. So every SLO you write go through the 4-part formula: metric, threshold, and window measurement. If you cannot fill in all 4, so you are not done yet. Not all SLOs are the same, and there are 5 categories that every serious system needs to define, and let me walk through them. The first category, that is the availability. This is the one everyone thinks of first. What percentage of the time is your system responding correctly, not just running correctly? And an HTTP 500 error does not count as availability, it counts as a failure. And if we talk about the category 2, and this is the latency, how fast does your system respond? and be specific about percentiles. P50 is the median, right? So half of the requests are faster, fee 99 means 99 out of 100 requests are faster, and that remaining 1% are your slowest users, right? They matter. In a system with 1 million users, the P99 represents 10,000 people having a bad experience, right? So it matters. And then we have the category 3. This is the durability. If someone writes data to your system, will it be there tomorrow? Will it be there in 5 years? Durability is about the permanence of stored data. This is separate from availability. Your system can be highly available but have poor durability if your backup system is broken. Then we have category 4, and that is throughput. How much work can your system handle before it starts degrading? This is directly connected to your estimation work from our last lecture. Your QPS, query per second, estimates sets your throughput requirement, right? So your throughput SLO makes that a formal commitment. And then we talk about the category 5, and that is the correctness. So does your system return the right answer? This one is often forgotten. A payment system that processes 100% of requests but charges the wrong amount occasionally has excellent availability but terrible correctness. So here is my practical advice. When you start a new system, define SLOs in all 5 categories from day 1. Even rough ones, even ones you know you might miss, starting with explicit targets and forcing the right conversations, right? So you cannot improve what you do. You cannot improve what you do not measure, and you cannot measure what you have not defined. Alright, so here is what I want you to do before the next lecture. Go to the system you are currently working on, or any system you know well, and write its SLOs, right? Start simple, define one SLI for availability, one for latency, one for durability. And before you pick targets, look at your incident history. How often has the system been down in the last 3 months? That gives you your baseline. Pick an SLO target that is slightly better than your current reality, and then something you are committed to achieving, not just aspiring to, right? So then calculate your error budget for each SLO, how many minutes of downtime you are allowed per month. What does that mean for how you deploy? Then do this thought experiment. What would break first if your load doubled tomorrow? Which SLO would you breach? That question will immediately show you where your architecture is weakest. And finally, look your current architecture and ask honestly, does it support the SLOs you just wrote? If the answer is no, you now have a concrete measurable engineering problem to solve. This is how professional architects work, not with vague goals like make it faster or improve reliability, with specific measurable commitments and a clear understanding of what it takes to meet them. In the next lecture, we bring everything together and we take our estimation skills from last lecture and our SLOs definition from this lecture, and we learn how to translate all of this into actual architecture decisions. So see you there. Thank you so much for watching this. Before you go, please don't forget to subscribe to my YouTube channel and turn on the notification bell so you never miss any of my upcoming videos. I regularly share valuable lessons, practical tips, and step-by-step tutorials to help you improve and grow. And if you are serious about mastering software design and architecture and want a complete structured learning experience, so I have created a full course that includes detailed lessons, assignments, quizzes, and downloadable workbooks to help you practice and apply what you learn. So if that sounds helpful, just check the link in the description below and enroll in the course today. I would love to see you inside and support you on your learning journey.